This training will introduce you to an observational tool that can be used to discern where aircraft turbulence is likely. I'm Scott Lindstrom from CIMSS. This machine learning product has been developed under the guidance of Tony Wimmers, using both ABI and AHI satellite data. Those instruments have sufficient horizontal resolution to resolve features that can be used to infer turbulence. The product is Probability of Moderate or Greater MOG Turbulence, and it was created using thousands of turbulent and non-turbulent events, clean window and upper-level water vapor infrared imagery, that is 10.3 and 6.2 micrometers, and aircraft-based observations of turbulence between 30,000 and 41,000 feet. The product also now incorporates mid- and upper-level GFS soundings. The product is probabilistic. What is the likelihood of moderate or greater turbulence for medium or large commercial aircraft, 737 or 777s respectively, at least once during a 10-minute period? Recall that 10 minutes is the routine full-disk scanning frequency for both GOES-R and Himawari. Water vapor imagery, band 8 at 6.2 micrometers on both GOES-R and Himawari, gives the best performance. So why use infrared window channel data at 10.3 micrometers? When the loop heat pipe cannot cool GOES-17 sufficiently, then band 8 imagery can cease giving useful information. In that case, band 13 still gives information that is almost as accurate as water vapor imagery. The window channel data is perhaps 5 to 10% less accurate, however, and regions of predicted turbulence for window channel detection tend to hug cloud features too much compared to water vapor detection of turbulence. The best detection of turbulence is with developing convection or with strong gravity waves that perturb clouds. You have poorer detection for gravity waves that emerge from jet stream shearing. That's even more so if the loop heat pipe malfunction is causing water vapor imagery to be missing. In other words, when only the window channel infrared data are available for turbulence detection. This product has been improved significantly since 2020. The 0.1 contour captures 70% of all turbulent events, but also contains 10% of observed non-turbulent events. Note that PODY on the y-axis means probability of a yes detection. The x-axis is 1 minus the probability of a no detection. The reliability diagram shown here shows a model with very low bias. N% probability zones experience about an N% frequency of moderate or greater turbulence. This is the MOG product contoured over water vapor imagery. Note the contribution from GFS data in featureless areas. There are also many contours over regions of satellite observed convection in this water vapor imagery. This infrared-only based product from 2 hours earlier than the previous image shows similar distributions and intensities, but it is more reliant on the GFS model. The product flags areas of intense gravity waves. It's contoured here over imagery operated on by a high-pass filter. Weaker gravity waves are not flagged. Here's an example of a very hard-to-detect event, one that does test the limits of the algorithm. This was isolated severe turbulence on board an Air Canada 777 that resulted in more than 25 injuries. It occurred over the Central Pacific. The contours, I'll show the animation in a bit, show MOG probability based on water vapor and infrared imagery only. No GFS data was included in this. The contours, I'll show the animation shortly, show MOG probability based on water vapor and infrared imagery only. For this case, GFS data were not included. The event occurred in the red circle and was associated with the first episode of convection that developed in the region. Let me show you the animation. It shows up only very briefly. The turbulence was occurring at this time. Very small probabilities were highlighted, however, in the region where the turbulence was occurring. It would be a challenge, to say the least, to use this product to alert for this event. There would be too many false alarms. This event highlights the challenge of detecting convectively forced turbulence. The product is available online. Click on the link. You can choose 3 different satellites, GO-16, GO-17, or Himawari, different hemispheres, northern or southern, regions within the map, parameters, probability of MOG turbulence or the high-pass filter, levels, 30 to 31,000, 32 to 33,000, and up to 40 to 41,000 feet, and also time. You can view one image or an animation. Use this site to monitor regions where you expect turbulence might be an issue. A couple of things to note. Turbulence often occurs on the edge of a predicted feature, not in the center. So if the aircraft skirts around the feature, it might not be moving into a region of no turbulence. If you see features that update hourly, that's the influence of the GFS. If you see features that evolve continuously, they are more likely satellite-influenced detections. Here's a summary slide. This deep learning algorithm uses upper-level water vapor for the best detection, and also uses window channel, still very good detection. GFS data are also included in the training. The parameter is probability of moderate or greater MOG turbulence. It's trained on flight level turbulence between 30 and 40,000 feet for large commercial aircraft. The model bias is very low, but estimated probability of MOG typically remains under 50%. That's the conclusion of this short training. Thanks for listening.